In this video, we examine contingency tables, specifically look at chi-square and other statistics that are used to analyze them. I'd like to use the childhood activity survey that we did in our evidence-based class. And specifically, we're going to create some categorical variables and look at them. One of the ones I would like to do, I would like to look at indoor and outdoor activity and test the association with whether or not a person is hyperopic or not. And so to do that, we didn't ask that specific question. Instead, we asked two questions regarding a person's sphere, cylinder axis for both the left and the right eyes. So what we're going to do is take the average. I've already calculated it here, so we're going to get a column that's going to look like that. But I want to walk through this just so that we have a little review of this. So let's go to transform, compute variable. And we put in our target variable as mean spherical equivalence. And then we're going to calculate the average spherical equivalence across both eyes. So OD sphere plus 0.5 OD cylinder plus OS sphere plus 0.5 times OS cylinder, and then we're going to divide that by 2, and that's going to give us an average. And so there it is. Now, what kind of distribution do we have? This is, 90-some optometry students, some extra graduate students thrown in. And what does our distribution look like? So let's go to Analyze, Descriptive Frequencies. There's our new variable. We're going to pick as a chart the histogram. We're going to not display our frequency tables because this is a continuous measure with zillions of different levels. We just want to look at the graph for an idea. And so we say OK. And we get a graph that looks like this. So this is 0. The mode, which is the most, is emmetropic at 0. And then it looks like it trails off. And it looks like we get kind of a little, potentially a little bump above -5, which are severe myopes. We could call them severe. -6 is usually the criteria. And on this way, it also goes down and then bumps up for what's probably hyperopes. Now, this is when I would really like for the scale to be a little bit more detailed. I wonder if we can do that. Let's try seeing if we can change our scale here. Let's go to scale, major increment 1, apply. Hey, look at that. So we bump up at 3. So even 2 or 3 is the key where we kind of find people. Let's use 2 as our cutoff for hyperopia, -1 for our cutoff for emmetropia, -5 for our cutoff for high myope. Actually, maybe -0.5 there. So what we want to do is we want to break down our mean spherical equivalence into a categorical variable. And the way we're going to do that is we're going to go to Transform. We're going to recode into a different variable. We're going to recode as mean spherical equivalence. We'll give it a new name, C. I usually, when I put variables categorical, I just put a C in front of it. So we have mean the category of mean spherical equivalents. Hit change so that this comes up here. And then our old and new values. So we're going to go the range. So there's a number of options. We can go value for value. We can even include system missing. We can give a range of variables. We can go lowest through highest and so forth. So we're going to do a range lowest. That's the lowest value. We don't have to give a name for it. Up to minus 5. And we're going to call that 1. I'm going to add it. And then we're going to go range. And we're just going to give minus 5 again because this works out all right on a continuous scale. Through, whoops, that's just 0.5. I want minus 5 through minus 0.05. I'm going to give that 2 and call that myopia. We're going to go minus 0.5 through 1, or 2. I'd say 2. 2. And we'll call that emetropia. 2 might be a little high. Oh well. And then from 2, we're going to range the value through the highest, which is 2. We're going to give that a value of 4. Okay, now we have those values. I'm going to double click on that database so we come into this, and I'm going to put in the values before I forget them. So 1 is a high hyperope. 2 is a, whoops, I didn't mean to say that, myope. 3 is an emetrope. 4 is a hyperope. All right. Now, how many of those do we have? Make sure we're got a reasonable number here. This one I'm not going to do a chart for, but I am going to display the frequency table. And so we have 25 high myopes, goodness. 39 myopes, 32 emetropes, and 7 hyperopes. All right. Now, we want to do crosstab. So what we're going to do for our crosstab is, we asked a question on the survey, was, as a 6 to 10-year-old child, were you mostly an indoor or outdoor child in terms of your daily activities? And then they could choose either indoor or outdoor. So let's do that question. Let's see if we can find it. I think it's right here. Question 25. Okay. So crosstabs is located under Analyze Descriptive Statistics, down here, crosstabs. And we're going to do Q25. And their mean spherical equivalent. I'm going to blow through this because I want to do something a little bit different. Let's just see what we get. We get a count, the numbers of people and everything here. But actually, before I do this kind of crosstab, let's do a 2x2 crosstab. So we're going to select cases if our category equals 2, or this little up and down thing is 2, or 3. Let's run our chi-square again. Analyze, descriptive, crosstabs, and then cells. We saw that before. It'll just give the numbers. So under cells, we have a choice of, we have the counts. Those are the observeds. We can look at expected. We can look at row percents, column percents, and so forth. Let's say a row percent, I believe, goes this way. So let's look at how many of each of these fell in that category. And then for statistics, we want the chi-square. And let's see what we get. Our chi-square value was not significant. We were not able to show in this example a difference between a significant association between myope, hemerope, and indoor-outdoor activity. We see that myopes were outdoors 56% of the time, and hemetropes were outdoors 62% of the time. A little bit more, but not really significantly. We could call this a sample size error, or sample size problem, but who knows? Now, what is the null hypothesis? The null hypothesis is that there is no association between indoor and indoor-outdoor variable and myopia-emetropia variable. So let's take a little bit more careful look at this output. We had 71 cases. There was no missing data. These are number of myopes, 17 and 22, percent of myopes who were indoor. That's percent within, C mean square spherical equivalent. That's 43, 54. We have our totals over here. We have this value right here, which is a chi-square value, 0.270. Just for a point of reference, note there is 1 degree of freedom. The mean of a chi-square distribution when the null hypothesis is true is 1. This value is less than 1. So we want this value to be greater than 1. And with 1 degree of freedom, this will be significant at the p less than 0.05 level if it is greater than 3.84. It isn't really too close to that. Thus, the significance is p-value is pretty high. So we have failed to reject the null hypothesis. We still haven't proved that they were significantly the same. Association was 0 basically, and in correlation terms. But we have shown there's not a significant association. Now, because we did a 2x2 table, there is the SPSS calculates the Yates continuity correction, and it's 0.077. Even less significant, that's a chi-square too, than the chi-square. The Yates continuity correction is more conservative. Fisher's calculates the exact test. It calculates a two-sided and a one-sided. We always do two. I don't know why they even print out the one, but it's a two-sided test. And it also shows no significant relationship between the two. All right, now let's go and select all our cases so we get the whole thing. And what we have, we don't actually have to change anything here. We just we have all the cases. Now it's gonna run three things. Here we go. Again, we got up over 1 anyway, but now the degrees of freedom in this 2 by 4 table are 3. Degrees of freedom are rows minus 1, 1, 2, 3, 4 rows minus 1 is 3, times columns minus 1. 1, 2 minus 1 is 1, 3 times 1 is 3, thus the degrees of freedom are 3. There's no continuity correction listed. We go straight down to the next value because it's not a 2 by 2 table. You only do continuity corrections on a 2 by 2 table, and honestly, you don't have to do them in either case. D'Agostino wrote a paper a few years ago suggesting that it was a waste of time to do that. Interestingly enough, he said that, well, I can't do that on this one. So we had 0.752. Let's go in, and I would like to show you one other thing. Unfortunately, this is not a very exciting finding. It is what it is, but it doesn't let me illustrate how cool expected things can be in this case. We have here, let's see, cancel. We have here this notion of expected. What is expected? You calculate the expected values by through the marginal totals. So we said 3 degrees of freedom. If you know these totals, 45, 58, 7, 32, 25, 39, if you know those, then when you have 3, you can change any 3 cells, but all the others are fixed. The expected value for this cell right here of 12 is 45 times 25 divided by 103. And let's look to see what that is. That's 10.9. And the chi-square looks at the observed 12 minus expected 10.9 and squaring that value, that's 1.1 squared, and then adding it to the next cell, 13 minus 14.1 squared, 17 minus, and so forth. The expected value is what you would get. It's kind of the average cell value by chance alone if there was no association. In other words, if the null hypothesis is true, you're going to get these expected values as the chance values. And so when you sum the difference between observed and chance, you're basically summing to see how different your observed values are from chance. And then you divide, after you've taken that difference, you divide it by the expected value, and you sum each of those little terms. Sum of the observed minus expected squared over expected, sum of the next one, plus sum of observed minus expected over expected, and so forth until you've gone through all 8 of them here. And that sum isn't very big in this case. It's a pretty small difference, wasn't significant, The more you sum, the higher your average is. So degrees of freedom, remember, are the mean of the chi-square distribution is equal to the degrees of freedom. So the mean of this distribution is 3. We only have 1.2. All right. I want to show you one more thing that is really pretty cool, though in this case doesn't make much difference. Let's go to Crosstabs, Cells, and I want to talk about standardized residuals. Now, the chi-squared in a 2x2 table, the chi-square value is equal to z squared. So if you take the square root of the chi-square value for a particular table, you will get the z-score. So we have all pretty small z-scores throughout here. We have 0.3, 0, because the count was 17, we expected 17, so it's right on the money. And down here it's 0.5. So if you multiply this observed 7 times the marginal, the 7 which is the total, times the marginal total of the column, 7 times 58, divided by the total 103, you will get this expected value. The observed 3 minus 3.9 divided by the square root of 3.9 is the standardized residual. So it takes the chi-square unit. Remember, it was observed minus expected squared divided by expected. So if you take the square root of that, you get observed minus expected. Square root of that is, or the squared. Well, anyway, it's just observed minus expected. And then in the denominator, you're not squaring it in the original, so you take the square root of it. And so it's 3 minus 3.9 divided by the square root of 3.9, and that turns out to be a minus 0.5. And if that number is greater than about 2, then you know that this cell is contributing to the deviation from expected values. When you have a chi-square that has many values and you get a significant chi-square, you don't know in here where the difference is. When you have a 2x2, it's much clearer where the difference is. But when the degrees of freedom are greater than 1, you don't know. So I think the standardized residual is a very useful statistic. The this adjusted standardized residual takes into account if these cell totals are very different. You could use it because this is kind of small relative to these others, which are reasonably in the same neighborhood. It's basically the same principle. The formula is just a little more complicated. All right, that's it.